You think you know volcanoes, mountains that explode, lava that burns, ash that falls, but beneath Earth's crust and beyond our planet, forces build that make Mount Vesuvius look gentle, volcanoes that hide a mile underwater, mountains that erupt ice instead of fire, mud that buries entire cities, calderas so massive they could swallow nations. Which ones kill without warning, and which ones have already changed your climate without you knowing? The term volcano covers structures so different they barely share a name. Shield volcanoes in Hawaii spread gentle slopes across hundreds of miles. Stratovolcanoes like Fuji build steep cones from alternating ash and lava. Cinder cones barely reach 1,000 feet, but number in the thousands across volcanic fields. Calderas collapse into themselves after eruptions so violent they empty chambers miles wide. Lava domes plug vents with rock so thick it can't flow. Submarine volcanoes number over 1 million beneath the ocean. Cryovolcanoes on distant moons erupt water and ammonia at temperatures cold enough to freeze steel in seconds. Mud volcanoes aren't even true volcanoes, but they've displaced 60,000 people in a single event. Every type follows its own rules. Every type carries its own threat. If you value documented geological history and planetary science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual. Using sources from the United States Geological Survey's Volcano Hazards Program publications, including their 2025 database update released September 30th, the National Park Service's Volcanoes, Craters, and Lava Flows technical documentation, and peer-reviewed articles from the Smithsonian Institution's Global Volcanism Program, which tracks 73 confirmed eruptions during 2024 alone from 65 different volcanoes. Now back to the information. Start with the giants. Shield volcanoes build the most massive mountains on Earth, but you'd barely know they're mountains. Mauna Loa in Hawaii rises 33,000 feet from the ocean floor to summit. That's taller than Everest measured from sea level, but the slopes angle less than 10 degrees. You could drive a car up most of it. The volcano spreads 60 miles across and contains 19,000 cubic miles of rock, all basalt, all from fluid lava that flows like motor oil when it erupts. The viscosity sits around 1,000 Pascal seconds, about 1,000 times thicker than water, but thin enough to travel 20 miles before cooling. Shield volcanoes form at hotspots and spreading centers where the Earth's crust pulls apart, or where mantle plumes punch through tectonic plates. The Hawaiian chain formed as the Pacific Plate drifted northwest over a stationary hotspot at about 3 inches per year. Each island marks where the hotspot built a volcano before the plate carried it away. Kilauea has erupted continuously or near continuously since 1983. Over 34 years, it poured out 1.3 cubic miles of lava. The flows buried 8 square miles of land under fresh rock and added 570 acres of new coastline to the island. Residents watched lava consume homes at walking speed. Temperatures reached 2,000 degrees Fahrenheit. The lava glowed orange through windows before walls collapsed inward. Shield volcanoes erupt frequently but gently by volcanic standards. No massive explosions, no pyroclastic flows traveling at hurricane speeds. The low gas content in basaltic magma means pressure builds slowly. When it breaks through, the lava fountains upward hundreds of feet, then settles into channeled flows. The 1984 eruption from Mauna Loa sent a flow toward Hilo that stopped just 5 miles from the city after 22 days. The flow advanced at speeds between 300 to 600 feet per hour at the front. Civil defense teams could track it by helicopter and predict which neighborhoods faced danger days in advance. That's the trade-off with shields. You see them coming, but you can't stop them. The lava consumes everything flammable and buries everything else under rock that takes centuries to weather back to soil. And the opposite extreme builds the postcard volcanoes. Stratovolcanoes, or composite volcanoes, form the steep, symmetrical cones that define the word volcano in most people's minds. Mount Fuji, Mount Rainier, Mount Mayon, these mountains stack alternating layers of lava, ash, pumice, and rock fragments over hundreds of thousands of years. The steep sides angle between 30 and 35 degrees. Some rise over 8,000 feet from base to summit in just a few miles of horizontal distance. The key difference is viscosity. Stratovolcanoes erupt andesite and dacite lavas with silica content between 57 and 68%. High silica means high viscosity, up to 100 million Pascal seconds. That's honey thick. The magma doesn't flow far before it cools and hardens. High viscosity creates high danger. A gas trapped in thick magma builds pressure like a shaken champagne bottle. When the pressure exceeds the strength of the overlying rock, the mountain explodes. Mount St. Horace, Helens, on May 18th, 1980s, blew its entire north face sideways. The lateral blast traveled at 300 miles per hour and flattened 230 square miles of forest. Trees up to 6 feet in diameter snapped like matchsticks. 57 people died, including volcanologist David Johnston, who was monitoring the volcano from a ridge 5 miles north. His last radio transmission at 8:32 a.m. read, "Vancouver, Vancouver, this is it." The blast reached him in seconds. Plinian eruptions, named after Pliny the Elder, who died observing Vesuvius in 79 AD, represent the most explosive events from stratovolcanoes. Mount Pinatubo in the Philippines erupted June 15, 1991, after 600 years dormant. Earthquakes announced the awakening in March. By June, thousands of small tremors shook the mountain daily. Scientists from the Philippine Institute of Volcanology and Seismology monitored the volcano with seismographs and predicted the major eruption with enough warning to evacuate tens of thousands of people from surrounding areas, including Clark Air Base, just 14 kilometers east of the summit. The climactic eruption lasted 9 hours. An ash column rose 28 miles into the atmosphere, into the stratosphere where jet airliners cruise. Pyroclastic flows, avalanches of superheated ash and gas, roared down the slopes at speeds exceeding 100 miles per hour. The flows filled valleys with deposits up to 660 feet thick. 400 square kilometers of land around the volcano was sterilized by the high temperature flows. The eruption ejected 5 cubic miles of magma. More critically, it blasted 20 million tons of sulfur dioxide into the stratosphere. The gas spread globally and formed a layer of sulfuric acid haze that circled the planet for years. Global temperatures dropped by half a degree Celsius from 1991 through 1993. The eruption of one mountain changed weather patterns worldwide. Pinatubo killed about 840 people. Most died when wet volcanic ash accumulated on roofs and caused them to collapse. Typhoon. Yunya crossed just 75 kilometers northeast of the volcano on the same day as the climactic eruption. The rain mixed with falling ash to create a heavy mud that weighed down structures. The evacuation saved at least 5,000 lives according to USGS estimates. Property damage reached $374 million in 1991 alone. Lahars, volcanic mudflows, continued for years afterward during every monsoon season. The loose volcanic deposits mixed with rainwater and flowed down valleys at speeds up to 30 miles per hour. The lahars buried entire towns and displaced over 100,000 people in the years following the eruption. Cinder cones represent the simplest volcano type: small, short-lived, built from a single vent. Most cinder cones stand less than 1,000 feet tall and form in a matter of days or weeks. Paricutin in Mexico provides the most documented case. On February 20th, through 1943, a farmer named Dionisio Pulido noticed his cornfield cracking and releasing sulfurous smoke. By the next morning, a cone had built to 30 feet. Gas-charged lava blasted violently into the air. The fragments solidified mid-flight and fell as cinders around the vent. The cone grew rapidly. Within a year, it stood 1,200 feet tall. The eruption continued 9 years before falling silent in 1952. Lava flows from the base buried the villages of Paricutin and San Juan Parangaricutiro. Only the church tower of San Juan emerged from the hardened rock. Cinder cones form when gas bubbles out of rising magma. The magma shatters into fragments that cool while airborne. The fragments range from fine ash to blocks the size of cars. They pile around the vent in loose stacks with slopes at the angle of repose, typically 30 to 40 degrees. The cones erode easily. Heavy rain cuts gullies down the sides within decades, but thousands exist. The San Francisco Volcanic Field in Arizona contains over 600 cinder cones spread across 1,800 square miles. Sunset Crater, one of the youngest, erupted around 1095 AD based on tree ring dating of wood burned by the lava flows. Now descend into the extreme. Supervolcanoes produce eruptions thousands of times larger than typical volcanic events. The term supervolcano describes volcanic systems capable of magnitude 8 eruptions on the Volcanic Explosivity Index. That means ejecting more than 1,000 cubic kilometers of material in a single event. To put that in scale, Mount St. Helens ejected 1 cubic kilometer. Pinatubo ejected 10 cubic kilometers. A VEI-8 eruption moves volumes 100 times larger. Yellowstone sits above one of Earth's most powerful volcanic systems. The Yellowstone caldera measures 53 by 28 miles across, but the walls only rise about 1,600 feet. It doesn't look like a volcano because it is a volcano. The caldera formed during the most recent super-eruption 640,000 years ago. That eruption ejected 240 cubic miles of ash, pumice, and rock. The Lava Creek Tuff, the deposit from that eruption, covers thousands of square miles across multiple states. Ash reached Louisiana and the Atlantic coast. The eruption column likely reached over 100,000 feet into the atmosphere. Yellowstone has produced 3 major super-eruptions in the past 2.1 million years. The first occurred 2.1 million years ago and ejected 600 cubic miles of material. The second happened 1.3 million years ago. Then the most recent, at 640,000 years ago. The intervals suggest a cycle of approximately 700,000 years between super-eruptions. That math worries some, but misleads more. The Yellowstone Volcano Observatory monitors the system constantly with seismographs, GPS stations, and satellite radar. The current inflation rate measures about 0.2 inches per year in some areas, slower than many other active calderas. The magma chamber sits 4 to 5 miles beneath the surface and contains about 4,000 cubic kilometers of partially molten rock. But only about 15% of that is liquid enough to erupt. The rest remains too solid to flow. A VEI-8 eruption would reshape continental climate. The 1991 Pinatubo eruption cooled global temperatures by half a degree for 3 years. A Yellowstone supereruption would eject dozens of times more sulfur dioxide. The immediate area within 600 miles would receive over 4 inches of ashfall, ash that thick collapses roofs. It clogs engines. It contaminates water supplies. It smothers crops. The ash cloud would spread globally within weeks and reduce sunlight reaching the surface. Growing seasons would shorten. Crop yields would plummet. Some estimates suggest global food production could drop by 10% for years. The USGS calculates the probability of another caldera-forming eruption at Yellowstone as roughly 1 in 730,000 per year. That's the same probability as a 1-kilometer asteroid hitting Earth. Other supervolcanoes scatter across the planet. Lake Toba in Indonesia formed from a super-eruption 74,000 years ago. That eruption ejected 700 cubic miles of material and created a caldera 60 miles long and 20 miles wide. Some researchers proposed the Toba eruption triggered a volcanic winter that pushed human populations to the brink of extinction, the so-called population bottleneck. The genetic evidence shows less certainty now, but the climatic impact must have been severe. The Valles caldera in New Mexico formed 1.2 million years ago from an eruption that produced the Bandelier tuff. The caldera spans about 13 miles across. The tuff deposits spread over 400 square miles, with thicknesses exceeding 300 feet in some areas. Submarine volcanoes outnumber land volcanoes by orders of magnitude. Estimates suggest over 1 million submarine volcanoes exist across the ocean floors. Perhaps 75,000 rise more than half a mile above the seafloor. Most form along mid-ocean ridges where tectonic plates spread apart at rates of 1 to 4 inches per year. The ridges extend 40,000 miles across the ocean floors like stitching on a baseball. Magma wells up through the central rift and solidifies to form new oceanic crust. The system operates continuously. Over half of Earth's volcanic activity happens underwater, where humans rarely witness it. Axial Seamount sits 300 miles off the Oregon coast, 1 mile beneath the Pacific surface. It's the most active submarine volcano in the Northeast Pacific, and the most monitored underwater volcano on Earth. Scientists installed the first instruments in 1997. The Ocean Observatory's initiative connected the seamount to shore with a fiber optic cable that transmits data in real time. Seismographs record every tremor. Pressure sensors track seafloor deformation. The volcano has erupted 3 times since monitoring began in 1998, 2011E, and 2015. Each eruption followed a similar pattern. The summit inflates as magma fills the chamber beneath. The inflation reaches a critical threshold. Then the volcano erupts, and the summit deflates by several feet as magma drains out. The pattern enabled scientists to forecast the next eruption. By late 2024, the summit had reinflated to 95% of the level seen before the 2015 eruption. Daily earthquakes numbered in the hundreds. Researchers predicted an eruption would occur between late 2024 and the end of 2025. By November 2025, the forecast window extended into 2026 as inflation rates slowed. Currently, the summit sits about 4 inches higher than immediately before the 2015 eruption, with potentially another 8 inches to go before reaching the critical threshold. If you value documented geological research and planetary science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script uses research from Oregon State University's Volcano World Database, updated January 2025, NOAA's volcanic monitoring programs tracking submarine volcanism, and peer-reviewed oceanography studies published in Nature documenting axial seamounts inflation patterns from 2015 through 2025. Now back to the information. Submarine eruptions create different hazards than land eruptions. When lava contacts water at depths below 7,200 feet, pressure prevents the water from boiling. The lava solidifies instantly into pillow lava, rounded masses that stack like sandbags. Above that depth, water can boil, and the interaction between magma and water creates steam explosions. The Hunga Tonga Ha'apai eruption on January 15, 2022, demonstrated the extreme end. The underwater volcano between Tonga and Fiji erupted with such violence, it blasted material 60 miles into the mesosphere, higher than any volcanic plume ever recorded. The explosion was heard in Alaska 5,000 miles away. The eruption triggered tsunami waves that reached 15 meters in Tonga and crossed the Pacific to cause flooding in California and Japan. The volcano injected 146 million tons of water vapor into the stratosphere, enough to temporarily increase stratospheric water content by 10%. The eruption killed 6 people in Tonga and caused an estimated $90 billion in damage globally. Most submarine eruptions pose little direct danger to humans because they occur in deep water far from shore, but they reveal processes happening continuously across the ocean floors. Seamounts like Axial serve as natural laboratories. Scientists study how magma rises and spreads. They measure gas emissions and chemical compositions. They map lava flows with autonomous underwater vehicles. Each data point improves the ability to forecast eruptions at more dangerous volcanoes on land. Now leave Earth entirely. Cryovolcanoes erupt ice instead of rock. The term describes volcanism involving volatiles like water, ammonia, and methane that freeze solid at the temperatures found in the outer solar system. Saturn's moon, Enceladus, hosts the most dramatic example discovered. Enceladus measures just 320 miles in diameter, about 1/7 the size of Earth's moon. But in 2005, the Cassini spacecraft photographed massive plumes erupting from the south polar region. The plumes shoot water ice, vapor, and organic molecules hundreds of miles into space at speeds exceeding 800 miles per hour. The eruptions release about 250 kilograms of material per second. That's 550 pounds per second continuously. The material feeds Saturn's E-ring, a diffuse ring of ice particles that extends from the orbit of Enceladus outward. The eruptions originate from 4 parallel fissures nicknamed the Tiger Stripes. The fissures cut about 80 miles across the south polar terrain. The ice along the fissures sits warmer than surrounding areas, about negative 120 degrees Fahrenheit compared to negative 320 degrees Fahrenheit elsewhere on the surface. Heat from tidal forces keeps a global ocean liquid beneath Enceladus's icy shell. The moon orbits Saturn every 33 hours. The tidal forces from Saturn's gravity flex the moon and generate heat through friction. The heat keeps water liquid beneath the ice crust. The plumes prove that liquid water connects to the surface through fractures in the ice. When Cassini flew through the plumes, it detected molecular hydrogen in the water. The hydrogen likely originates from hydrothermal reactions between the ocean water and the rocky core. Hydrothermal vents on Earth support entire ecosystems without sunlight. The chemistry detected at Enceladus suggests similar conditions might exist in its subsurface ocean. The discovery made Enceladus one of the most promising locations in the solar system to search for extraterrestrial life. Jupiter's moon. Europa shows similar, but less active cryovolcanism. Europa measures 1,940 miles across, slightly smaller than Earth's moon. Its surface consists of water ice covering a subsurface ocean estimated at 60 to 90 miles deep. That's more liquid water than all of Earth's oceans combined, despite Europa's smaller size. The Hubble Space Telescope detected possible water vapor plumes erupting from Europa's surface during observations in 2012, 2014, and 2016. The plumes appeared near a thermal hotspot detected by the Galileo spacecraft in 1999. The hotspot suggests either very thin ice or a reservoir of liquid water trapped within the ice shell. If the plumes are real, and their detection remains debated, they would offer a way to sample Europa's ocean without drilling through miles of ice. Neptune's moon Triton also shows evidence of cryovolcanic activity. When Voyager 2 flew past Triton in 1989, it photographed dark plumes rising from the surface. About 50 plume sites were visible. The plumes reached 5 miles high before winds carried them horizontally across the surface. The temperature on Triton averages negative 391 degrees Fahrenheit, cold enough to freeze nitrogen solid. The plumes likely consisted of nitrogen gas driven by solar heating. Sunlight penetrates the translucent nitrogen ice and warms the darker subsurface material. The warming vaporizes the nitrogen, which builds pressure until it breaks through the surface like a geyser. The dwarf planet Pluto revealed possible cryovolcanoes during the New Horizons flyby in July 2015. Wright Mons and Pickard Mons are 2 large mountains with summit depressions that resemble volcanic calderas. Wright Mons spans 90 miles across and rises about 13,000 feet. If Wright Mons is indeed a cryovolcano, it would be the largest ice volcano discovered in the solar system. The mountains appear relatively crater-free, suggesting recent formation, perhaps within the last few million years. The frigid temperatures on Pluto, negative 380 degrees Fahrenheit, mean any cryomagma would consist of materials like ammonia and methane mixed with water ice. Mud volcanoes erupt mud instead of molten rock. They're not true volcanoes because they lack magmatic heat, but they form volcanic-looking cones and can produce violent eruptions. About 1,100 mud volcanoes have been identified on land and in shallow water. Estimates suggest over 10,000 exist on continental slopes and abyssal ocean plains. Mud volcanoes form when sediments suspended in fluids are pressurized by tectonic activity or by accumulation of hydrocarbon gases. The pressure forces the mud upward through faults and fractures. Most mud volcanoes stand just a few meters tall, but the largest reach hundreds of meters high and span miles across. Azerbaijan hosts nearly 400 mud volcanoes, more than half the world's total. The Lokbatan mud volcano near Baku erupts approximately every 3 to 5 years, making it possibly the most active mud volcano on Earth. The eruptions produce gas flares that reach over 300 feet high and eject thousands of cubic meters of mud breccia. The flows extend over a mile from the central crater. The mud consists of clay minerals mixed with water and methane gas. The methane is flammable. When it ignites during eruptions, it creates spectacular fire fountains visible for miles. The Lucy mud volcano in Indonesia began erupting on May 29, 2006, near the town of Sidoarjo in East Java. The eruption started with steam venting from a ruptured ground surface. Within weeks, the site was spewing hot mud and natural gas. The flow rate peaked at 180,000 cubic meters per day. The mud spread across the countryside, engulfing villages and farmland. The Indonesian government built a series of levees to contain the flow. When the mud overtopped the first levees, they built new ones behind them. The eruption forced 60,000 people to relocate permanently. By the time the flow was contained, it had buried 12 villages under mud deposits up to 100 feet thick. The cause of the Lucy eruption remains debated. One camp argues that an exploratory gas well drilled by Lapindo Brantis destabilized underground formations, allowing pressurized fluids to escape. The well was drilled to 9,300 feet without installing proper casing in some sections. 2 days before the eruption began, Sinon, drilling mud was lost into the formation, suggesting the drill had intersected a high-pressure zone. The other camp argues that a magnitude 6.3 earthquake that struck 170 miles away 2 days before the eruption triggered the failure. Analysis of drilling records showed no loss of mud circulation into Lucy itself, and pressure tests after the eruption found the wellbore intact. The Indonesian Supreme Court dismissed a negligence lawsuit against Lapindo Brantis in 2009, citing lack of evidence. Lucy continues erupting, but at much slower rates. As of 2022, the flow had decreased to about 10,000 cubic meters per day. The mud deposits remain hot internally. Temperatures exceeded 900 degrees Fahrenheit in some deposits 5 years after the eruption began. When water contacts these hot deposits, they explode and spread fine ash. The mud volcano has provided scientists a rare opportunity to study an active eruption in detail. Core samples reveal the mud originates from clay formations at depths of over 6,000 feet. Chemical analysis shows the water was heated by a magma chamber associated with nearby volcanic complexes. Lava domes form when highly viscous magma squeezes out of a vent like toothpaste from a tube. The magma is too thick to flow far, so it piles up around the vent, creating a steep-sided dome. Mount St. Helens built a lava dome in its crater after the 1980 eruption. The dome grew episodically from 1980 to 1986 as fresh magma rose from depth. The dome reached over 800 feet tall and more than 3,000 feet across before stopping. Lava domes can be dangerous because they're unstable. The steep sides can collapse, triggering pyroclastic flows. Dome collapse at Mount Unzen in Japan during 1991 generated pyroclastic flows that killed 43 people, including volcanologists Harry Glicken and Kadia and Maurice Kraft, who were documenting the eruption. Fissure volcanoes erupt along linear cracks rather than from a central vent. Iceland hosts numerous fissure eruptions along the mid-Atlantic ridge, where the North American and Eurasian plates pull apart. The Laki Fissure opened in June 1783 and erupted continuously for 8 months. The fissure extended 16 miles and created over 130 craters along its length. The eruption poured out 3.4 cubic miles of basaltic lava that covered 220 square miles. More critically, the eruption released 8 million tons of fluorine gas, which poisoned livestock across Iceland. The resulting famine killed about 21% of Iceland's population, approximately 9,600 people. The sulfur dioxide emissions created a haze that spread across Europe and caused crop failures. The global climate anomaly contributed to food shortages that historians link to the social unrest preceding the French Revolution. The Reykjanes Peninsula in Iceland has experienced a series of fissure eruptions since 2023 near the town of Grindavik. The eruptions have produced lava fountains and flows of basaltic lava but remain relatively small. The flows have damaged roads and infrastructure, forcing periodic evacuations, but have not caused any deaths. The eruptions demonstrate how fissure volcanism can persist in an area with multiple events occurring over months or years. Caldera volcanoes produce the most destructive single events. Calderas form when the magma chamber beneath a volcano empties during an eruption. The overlying rock loses support and collapses into the void, creating a massive depression. Crater Lake in Oregon fills a caldera that formed about 7,800 years ago when Mount Mazama erupted and lost its summit. The eruption ejected about 12 cubic miles of rhyolitic magma, creating an ashfall that reached Alberta, Canada. The caldera measures 6 miles across, and the lake that filled it reaches 1,923 feet deep, making it the deepest lake in the United States. Santorini in Greece erupted around 1600 BC in one of the largest volcanic events in recorded human history. The Minoan eruption ejected 14 cubic miles of material and created a caldera that now forms a bay filled by the Mediterranean Sea. The eruption buried the Bronze Age settlement of Akrotiri under volcanic ash, preserving it similar to how Pompeii was preserved. The eruption generated tsunami waves that devastated coastal settlements around the Aegean Sea. Some historians link the eruption to the decline of the Minoan civilization on Crete and speculate it inspired the legend of Atlantis, though both connections remain debated. The scale differences across volcano types create different threat patterns. Shield volcanoes like Mauna Loa produce massive lava flows that can be tracked and avoided but destroy everything they contact. Stratovolcanoes like Pinatubo generate explosive eruptions with pyroclastic flows that travel at hundreds of miles per hour and cover massive areas in minutes. Submarine volcanoes mostly erupt unnoticed but can trigger destructive tsunamis when they break the surface violently. Cryovolcanoes on distant moons reveal how volcanism operates under exotic conditions, where water acts like molten rock. Mud volcanoes aren't powered by magma, but can still bury entire regions in unstoppable flows of pressurized sediment. The monitoring networks have improved dramatically. Seismographs detect earthquakes caused by magma movement. GPS stations measure ground deformation as magma chambers inflate. Gas sensors track emissions of sulfur dioxide and carbon dioxide, which increase before eruptions. Satellite radar can detect centimeter-scale changes in elevation across entire volcanic regions. Thermal cameras on satellites detect heat signatures from active lava flows and eruption clouds. The combination allows volcanologists to issue warnings days or weeks before major eruptions at well-monitored volcanoes. The success at Pinatubo in 1991, where scientists forecast the eruption with enough lead time to evacuate tens of thousands of people, stands as proof the technology works. But gaps remain enormous. Most of the world's 1,500 active volcanoes lack monitoring equipment. Small volcanic islands in remote areas have no permanent instruments. Even well-monitored volcanoes can surprise. Mount Ontake in Japan erupted without warning on September 27, 2014, killing 63 hikers who were on the summit when the Friedik explosion occurred. The volcano had shown no notable seismic activity, and the eruption gave no clear precursor signals. Phreatic eruptions, steam explosions driven by groundwater contacting hot rock rather than magma rising to the surface, are particularly difficult to forecast because they don't follow the same patterns as magmatic eruptions. The volcanic winter scenario from a super-eruption represents the extreme tail risk. The Toba eruption 74,000 years ago and the Yellowstone eruptions demonstrate that single volcanic events can alter global climate for years. The sulfur dioxide emissions form sulfuric acid aerosols in the stratosphere that reflect sunlight back to space. The cooling effect persists until the aerosols settle out, which takes several years. A Vi 8 eruption would cool temperatures enough to severely disrupt agriculture across multiple continents. The social and economic impacts would cascade globally in ways difficult to model, but certainly catastrophic. The volcanic record stretches back millions of years. The Siberian traps erupted 252 million years ago at the end of the Permian period. Over a span of perhaps a few 100,000 years, massive flood basalt flows covered 700,000 square miles of Siberia under layers of lava up to 2 miles thick. The eruptions released enormous volumes of carbon dioxide and sulfur dioxide. The climate disruption coincided with the Permian-Triassic extinction event, the worst mass extinction in Earth's history, which eliminated about 96% of marine species and 70% of terrestrial vertebrate species. The Deccan Traps in India erupted 66 million years ago around the time of the Cretaceous Paleogene extinction event that killed the non-avian dinosaurs. The flood basalts covered 200,000 square miles and reached over 6,000 feet thick in some areas. The eruptions spanned approximately 750,000 years, with the most intense phases potentially overlapping with the Chicxulub asteroid impact in Mexico. Whether the Deccan volcanism contributed significantly to the extinction or whether the asteroid impact was the primary cause remains actively researched, but both represent catastrophic global-scale events. The Earth's volcanic systems remain active. About 50 to 70 volcanoes erupt each year. Most eruptions last days to weeks. A few continue for years or decades. Eruptions in remote areas often go unnoticed until satellite observations or aircraft reports detect the ash clouds. The Global Volcanism Program tracks eruptions worldwide and maintains a database of Holocene volcanoes, those that erupted in the past 10,000 years. The database includes over 1,500 volcanoes on land. The submarine volcano count remains uncertain because large areas of ocean floor have never been mapped at sufficient resolution to identify individual seamounts. On Mars, the largest volcano in the solar system dwarfs anything on Earth. Olympus Mons rises 16 miles above the surrounding plains and spans 374 miles across at its base. That's about the size of Arizona. The mountain is a shield volcano that built up from countless eruptions over hundreds of millions of years. Mars lacks plate tectonics, so the volcano remained stationary over its hotspot, unlike the Hawaiian chain where plate motion carries volcanoes away from the hotspot. Olympus Mons shows no signs of recent activity, but the surface appears relatively young, suggesting the last eruptions occurred within the past few million years, geologically recent. Venus hosts over 1,600 major volcanoes and possibly thousands more smaller cones. The planet's thick atmosphere makes observations difficult, but radar mapping from the Magellan spacecraft in the 1990s revealed a landscape dominated by volcanic features. Most scientists think Venus remains volcanically active, but no eruption has been confirmed directly. Recent studies analyzing infrared data suggest some volcanic regions show heat signatures consistent with fresh lava flows from the past few decades. Io, Jupiter's innermost large moon, holds the record for most volcanically active body in the solar system. Tidal heating from Jupiter and the other Galilean moons keeps Io's interior molten. Sulfur dioxide eruptions vent continuously across the surface. The Voyager spacecraft photographed massive volcanic plumes in 1979. The Galileo spacecraft detected over 150 active volcanic centers during its mission from 1995 to 2003. The lava erupting on Io reaches temperatures above 2,700 degrees Fahrenheit, hotter than lava on Earth. The volcanism resurfaces Io so rapidly that impact craters disappear within a few million years, making it the youngest surface in the solar system. Every volcano operates by moving material from depth to surface, but the mechanisms and materials vary wildly across the spectrum. Basaltic magma with low viscosity and low gas content produces gentle eruptions that build shield volcanoes. High silica magma with high viscosity traps gas and produces explosive eruptions that build stratovolcanoes and calderas. Water mixing with magma at shallow depth creates phreatic explosions. Cryomagma, consisting of water, ammonia, and methane, erupts on icy moons where surface temperatures would freeze rock solid. Pressurized mud and gas creates mud volcanoes without any magmatic involvement. The classification systems group volcanoes by morphology, by eruption style, by tectonic setting, by composition. Each system captures different aspects of the same underlying physics. Heat drives buoyancy, buoyancy drives ascent, ascent drives eruption. The human timeline intersects volcanic activity at random. Vesuvius in 79 AD buried Pompeii and Herculaneum. Tambora in 1815 caused the year without a summer that brought crop failures and famine across Europe and North America. Krakatoa in 1883 produced a tsunami that killed over 36,000 people and an ash cloud that circled the globe. Novarupta in 1912 ejected more material than any other 20th century eruption. Pinatubo in 1991 demonstrated modern forecasting capabilities. Eyjafjallajökull in Iceland in 2010 grounded air traffic across Europe for weeks because the ash cloud threatened jet engines with stone particles that could cause catastrophic mechanical failure. The 2018 eruption of Kilauea destroyed over 700 homes in Lower Puna on the Big Island of Hawaii. Fissure 8 opened on May 27th and poured out fast-moving lava for 3 months. The flow entered the ocean and created a plume of lava haze, formed when molten rock contacts seawater and creates hydrochloric acid vapor. The eruption also drained the Summit lava lake, triggering collapse events that created a caldera depression over 1,600 feet deep. The ground shook with thousands of earthquakes. Some reach magnitude 5.3. The patterns emerge across the data. Volcanoes near subduction zones erupt explosively. Volcanoes over hotspots and spreading ridges erupt more gently. Magma viscosity controls eruption style more than any other single factor. Gas content determines explosivity. The time between eruptions often correlates with the violence of the next eruption because longer repose periods allow gas and pressure to build. Volcanic systems with short repose periods like Stromboli or Kilauea bleed off pressure continuously through frequent small eruptions. Systems with long repose periods like Pinatubo can accumulate massive amounts of magma and gas before failing catastrophically. The question isn't whether volcanoes will erupt, but when and where. The mid-ocean ridges spread continuously, adding new crust at rates measured in inches per year. The process is volcanic, even if no spectacular eruption marks it. Hotspots like Hawaii punch through plates regardless of plate motion. Subduction zones, where one plate dives beneath another, generate arc volcanoes as water released from the subducting plate lowers the melting point of the overlying mantle. The Ring of Fire encircling the Pacific Ocean hosts about 75% of the world's active volcanoes because most of the Pacific boundary consists of subduction zones. On the night of October 9, 2024, Iwistag, Lewitobi Laki-Laki volcano in Indonesia erupted without clear warning. The eruption killed at least 10 people in nearby villages. Volcanic ash fell across the region, grounding flights and blanketing homes. The event demonstrated that even monitored volcanoes in densely populated areas remain capable of deadly surprises. Indonesia contains 127 active volcanoes, more than any other country, because it sits where the Indo-Australian plate subducts beneath the Eurasian plate along the Sunda Arc. The subduction creates the chain of volcanic islands that form Indonesia's archipelago. A drilling rig probes the seafloor off New Zealand's North Island. The target sits 2,500 feet beneath the ocean surface and another 1,600 feet into the rock below. The project seeks to extract cores from the Havre submarine volcano, which erupted in 2012. The eruption created the largest deep ocean pumice raft ever documented, a floating mass of rock fragments that covered over 150 square miles. The pumice drifted across the Pacific for years, carrying marine organisms to new locations. The cores will reveal the sequence of events during a submarine eruption and test hypotheses about underwater volcanic processes. Scientists found sulfur deposits on Wright Mons on Pluto. The sulfur likely came from volcanic degassing, but the temperatures on Pluto sit so cold that sulfur should be frozen solid under normal conditions. The presence of sulfur in locations suggesting fluid transport implies that cryovolcanic processes on Pluto involve more complex chemistry than simple water ice. Perhaps ammonia acts as antifreeze, lowering the melting point enough for liquid flows at Pluto's surface temperatures. Perhaps internal heat from radioactive decay in the core drives convection in the icy mantle. New Horizons passed Pluto at 14,000 miles per hour, giving just hours of close observations. The images raise more questions than they answer, but they prove that volcanism extends to the coldest reaches of the solar system. Ash from the 1729 eruption of Lanzarote in the Canary Islands buried fertile farmland under feet of volcanic material. The islanders developed a unique agricultural system. They dug pits through the ash layer down to the buried soil, then planted crops in the pits. The ash layer acts as mulch. It absorbs dew overnight. It reduces evaporation during the day. The system called Enharinado allows viticulture in a near-desert environment. The Malvasia wines produced from those volcanic soils became renowned across Europe. The technique demonstrates how volcanic disasters force innovation. The same ash that destroyed the original agriculture created conditions for a new agriculture more suited to the arid climate. Volcanic soils weather into some of the most fertile farmland on Earth. The minerals in basalt and andesite break down over centuries into clays and nutrient-rich soils. The slopes of Mount Vesuvius support intensive agriculture despite sitting in the direct shadow of a volcano that has killed thousands. The population density around Vesuvius exceeds 3,000 people per square kilometer because the volcanic soils produce high yields. The risk-reward calculation plays out across volcanic regions worldwide. The hazard remains constant, but the economic benefit of the rich soils draws settlement. Heat from magma chambers drives geothermal systems that provide renewable energy. Iceland generates about 30% of its electricity from geothermal power plants that tap water heated by volcanism. The geysers in California, the largest geothermal field in the world, supplies electricity for hundreds of thousands of homes by piping steam from hot rock to turbines on the surface. Kenya's Olkaria geothermal complex near the Rift Valley generates over 800 megawatts tapping heat from volcanic systems beneath. The resource requires volcanism to exist, but volcanism brings eruption risk. The balance defines the relationship between humans and volcanic systems. On Mars, the absence of plate tectonics allowed volcanoes to grow to sizes impossible on Earth. On Earth, plate motion carries volcanoes away from their magma sources, limiting how large any individual volcano can grow. The Hawaiian Islands demonstrate the pattern. Each island built until the plate carried it northwest, and a new island began forming over the stationary hotspot. The current island, the Big Island, contains 5 volcanoes at various stages of activity. The next island, Loihi, grows undersea about 20 miles southeast of the Big Island. It already rises over 10,000 feet from the ocean floor, but its summit remains 3,000 feet underwater. In perhaps 50,000 years, Loihi will breach the surface and begin building a new island. A seismograph at Mount Rainier records a small earthquake. The tremor registers magnitude 1.2. The event occurred 7 miles beneath the summit. Analysis shows it's a volcanotectonic earthquake caused by magma or fluids moving through fractures in the rock. The earthquake is one of dozens detected beneath Rainier each year. Individually, they mean little, but a sudden increase in earthquake frequency or a change in the depths where earthquakes cluster would signal that magma is rising, and an eruption might follow. Mount Rainier stands 54 miles southeast of Seattle and 43 miles northeast of Tacoma. The volcano rises 14,410 feet and supports 25 named glaciers containing as much ice as all other Cascade volcanoes combined. An eruption would likely trigger massive lahars as pyroclastic flows melt ice. The lahars would follow river valleys that contain towns and infrastructure. Hazard maps show flow paths extending into the Puyallup River Valley, which empties into Tacoma's port. Over 150,000 people live in areas that could be inundated by lahars from a large eruption. Risk doesn't equal hazard. Volcanoes on remote islands pose minimal risk regardless of their explosive potential because few people live nearby. Volcanoes near major cities pose extreme risk even if their eruptions are relatively small. Mount Vesuvius looms over Naples, which has a metropolitan population exceeding 3 million. The volcano last erupted in 1944. That eruption destroyed the village of San Sebastiano and killed 27 people. The event was relatively small. A larger eruption following historical patterns like the Plinian eruption in 79 AD would impact hundreds of thousands of people. Italian authorities have developed evacuation plans, but moving 3 million people requires days of notice and depends on accurate eruption forecasting. The core of a shield volcano in Hawaii shows how these structures build. Drill cores from the Hawaii Scientific Drilling Project penetrated over 10,000 feet through volcanic rock and revealed the internal structure. The rock consists almost entirely of thin lava flows, each only a few feet thick. The flows stack atop one another like pages in a book. Some layers show evidence of weathering on their upper surfaces, indicating pauses between flows that lasted long enough for soil to develop. Other layers show no weathering, indicating they were buried by subsequent flows shortly after they cooled. The drilling demonstrated that shield volcanoes grow primarily through accumulation of countless small flow events rather than a few massive eruptions. Seismic tomography, using earthquake waves to image Earth's interior like a medical CT scan, reveals the structure beneath volcanic regions. Beneath Yellowstone, the imaging shows a plume of hot rock rising from the mantle 600 miles deep. The plume feeds the magma chamber beneath the caldera. Beneath Hawaii, the imaging shows a similar plume extending even deeper, perhaps to the core mantle boundary. These mantle plumes remain stationary while tectonic plates move above them, creating chains of volcanoes that record the plate motion. The hotspot hypothesis explains volcanic features like the Hawaiian Emperor Seamount chain and the Yellowstone Snake River Plain volcanic field. The chemistry of erupted lava reveals information about depth and conditions in the magma chamber. Basaltic magmas form by partial melting of the upper mantle at depths between 30 and 60 miles. The basalt composition reflects the source rock, primarily peridotite, rich in olivine and pyroxene. Andesitic magmas form either by partial melting of hydrated mantle above subduction zones or by fractional crystallization of basaltic magma, where dense minerals sink out, leaving silica-enriched melt. Rhyolitic magmas form by extreme fractional crystallization or by melting of crustal rocks. The progression from basalt to andesite to rhyolite represents increasing silica content, increasing viscosity, and increasing explosivity. Satellite technology transformed volcano monitoring. The Landsat program has imaged Earth's surface since 1972. The continuous record allows detection of changes in volcanic regions. Thermal infrared sensors on satellites can detect heat from active lava flows in volcanic vents day or night through clouds. Synthetic aperture radar can measure ground deformation with centimeter precision. The measurements reveal inflation and deflation of volcanoes as magma moves beneath the surface. The combination of satellite and ground-based monitoring provides unprecedented coverage. Volcanoes that previously lacked monitoring now appear in global datasets updated weekly or daily. Every extreme volcano type reveals fundamental principles about how Earth and planetary systems operate. Heat drives buoyancy. Buoyancy drives convection. Convection transfers heat from deep interiors to surfaces. At surfaces, the heat releases through volcanism in forms determined by composition, pressure, temperature, and the presence of volatiles. Understanding these systems improves hazard assessment. It informs decisions about where to build cities and infrastructure. It guides emergency response planning. It contributes to basic science about planetary evolution. The record shows that major volcanic events have altered human history. The massive Minoan eruption 1700 years before Christ collapsed to civilization. The Laki eruption helped trigger social upheaval in 18th century Europe. Tambora caused global crop failures in 1815. Krakatoa in 1883 killed tens of thousands and affected weather worldwide. Pinatubo in 1991 cooled the planet and proved forecasting works when instruments and expertise combine. The 2018 Kilauea eruption destroyed 700 homes, demonstrating that even well-studied, frequently active volcanoes can surprise with their intensity. Behind the eruptions lie deep processes. Subducting slabs carry water into the mantle. The water lowers rock melting points, generating magma that rises through the overriding plate. Hotspot plumes punch through plates from deep mantle sources, creating volcanic chains. Spreading ridges pull apart, allowing mantle to rise and melt, generating new crust. Each tectonic setting produces characteristic volcanism. Each volcano type reflects specific conditions of temperature, pressure, and composition. In 2025, researchers drilling into the Chicxulub impact crater in Mexico retrieved cores from the Peak Ring, the innermost ring of mountains created by the asteroid impact 66 million years ago. The cores show that the impact melted and shocked rock to incredible pressures. But they also show that life returned quickly. Within years, microorganisms colonized the crater. Within centuries, the crater hosted a thriving ecosystem. The recovery demonstrates resilience. Volcanic eruptions create similar destruction on regional scales. The recovery follows similar patterns. Ecosystems adapt, humans rebuild, the volcanic landscapes that once supported no life become fertile grounds again. Monitoring networks now span the globe, connecting instruments to central databases. The USGS manages the National Volcano Early Warning System, covering volcanoes in U.S. territories. The Smithsonian Institution's Global Volcanism Program maintains comprehensive eruption records. NOAA's volcanic ash. Advisory centers track ash clouds that threaten aviation. The data streams continuously. Earthquakes trigger automatic alerts. Ground deformation exceeding thresholds prompts investigations. The systems work when funding supports them and when expertise exists to interpret the signals. Budget cuts and personnel shortages remain constant challenges. Volcanic monitoring requires sustained commitment across decades between eruptions to provide useful warnings when eruptions threaten. The future holds certainty. Volcanoes will erupt, some eruptions will kill people and destroy property, some will disrupt aviation and agriculture. A few will alter global climate. The timing and locations remain uncertain, but the patterns suggest where risk concentrates. Subduction zones, particularly the Pacific Ring of Fire. Hotspots like Hawaii, Iceland, and Yellowstone. Rift zones like the East African Rift. The question facing societies is how much to invest in monitoring and what level of risk to accept in exchange for the benefits of living near volcanoes. Io continues erupting. Enceladus continues jetting water into space. Earth's mid-ocean ridges continue spreading. The volcanic systems that built planets continue operating. The moon. Io will someday cool enough that its volcanism ceases. The sun will expand into a red giant engulfing Mercury, Venus, and possibly Earth-ending volcanism on those worlds, but billions of years remain before then. In human timescales, volcanism remains as permanent as mountains and oceans. On Reunion Island, east of Madagascar in the Indian Ocean, Piton de la Fournaise erupts again. The eruption began early morning, October 30th, 2024. Lava fountains at the summit. Flows cascade down the southeast flank. The eruption rate peaks at 100 cubic meters per second. The flows advance at walking pace, heading toward uninhabited areas. Authorities close hiking trails, but no evacuations are needed. The volcano erupts every 1 to 3 years. Monitoring stations detected increased seismicity 3 days before the eruption began, giving ample warning. The eruption provides another data point, another chance to study how basaltic systems operate, another reminder that volcanism continues regardless of whether humans notice. A drilling project in Iceland aims to tap magma directly. The Iceland Deep Drilling Project seeks to reach magma chambers and extract heat at temperatures exceeding 800 degrees Celsius. Previous projects accidentally drilled into magma at shallower depths than expected. The rock was molten. It flowed into the drill hole. The temperatures exceeded the design limits of standard geothermal equipment. Engineering solutions are being developed to handle the extreme heat. If successful, the project could extract orders of magnitude more energy than conventional geothermal systems that tap hot water rather than magma. The intersection of volcanic research and energy technology demonstrates how understanding volcanism leads to practical applications. Every volcano on Earth formed by processes that extend across the solar system. The same physics that builds Mauna Loa built Olympus Mons. The same chemistry that erupts basalt on Earth erupts sulfur on Io. The same fractures that channel magma on stratovolcanoes channel cryomagma on Enceladus. Understanding volcanism in all its forms reveals how planets live and how they die. The monitoring continues. The research advances. The eruptions occur. And humans adapt to living on a planet that remains geologically active 4.5 billion years after formation.